We're now moving on to 17.2, galvanic cells. Here we're going to describe the function of a galvanic cell and its components, and use cell notation to symbolize the composition and construction of galvanic cells. So let's first think of adding a piece of copper metal to a solution with silver ions. What happens is a replacement reaction, a single replacement reaction, in which the copper dissolves to become copper 2 plus ions, and the silver actually precipitates out as solid silver. So if you were to do this directly in a test tube, the silver metal deposits on the surface of the copper metal strip. And then the copper enters the solution and becomes this beautiful blue copper 2 ion solution. But what if we made it so that for the electrons to transfer, they have to pass through an external wire? So this is the system I was just describing. The silver solution is clear, but when you add in some copper metal, that replacement reaction happens, and so the solution turns blue from the copper, and you can see the silver metal kind of coating the copper, and some of it's even fallen off on the bottom. So let's talk about galvanic cells. So galvanic cells is what this whole section and pretty much the whole chapter is about. And these are essentially batteries. And we use spontaneous redox reactions to serve as a source of electrical energy in a galvanic cell. So we're able to harness the flow of electrons for energy. So the cell takes advantage of the movement of electrons, which happens during a redox reaction. And what happens is we take the half reactions from the redox and we compartmentalize them into half cells. So you have two sides where you have one electrode, which has your anode, where oxidation happens, and your other side, which is your cathode, where reduction happens. And there's a wire that connects those two, and the electrons are going to move from the anode to the cathode. So generally the way we draw this is anode on the left, cathode on the right. And so we use these moving electrons as a source of electrical energy. So the oxidation and reduction half reactions occur at separate electrodes. Again, the oxidation happens at the anode, so the anions are going to the cathode, and the reduction happens at the cathode, where cations are flowing to the cathode. Okay, so cat goes to cat, an goes to an. So this is a galvanic cell that you can make in a lab. You have your anode, so in this case we have a copper anode. So this is just a piece of copper metal, and it's immersed in a solution with copper 2 plus. So it's in a 1 molar solution of copper 2 nitrate. And then you have on your cathode side, you have a silver anode, so this piece of silver metal in a 1 molar solution of silver nitrate, which gives us some silver plus and nitrate. So the nitrate here, the NO3 minus, is just a spectator ion. Notice it's in both solutions. It's not doing anything. But what's also happening is we have this salt bridge that's made of sodium nitrate. So it is also going to, it basically keeps the reaction going. It gives some positive ions to the cathode side, and negative ions from it go to the anode side, which is why you see the sodium plus and NO3 minus. Okay, so at the same time, the anions from your solutions are flowing from the cathode to the anode side, whereas your cations are going to the cathode side. And the electrons, again, are going from anode to cathode. So this is a galvanic cell. So notice also each side in the cell has the redox conjugate pairs of a single reaction. So you have the copper 0 So you have the copper going to copper 2+, and the silver and silver plus. So you have both the half reactions that are occurring. Technically, one's the opposite reaction, but you have the half cells on each side. Technically, this is copper. There's just silver 1 going to silver 0. There we go. So the copper metal and the silver metal are called electrodes. And then here's that reaction that's happening. The external wires that also help with the flow of electrons, we connect to a voltmeter, which tells us the voltage or the amount of charge that's being transferred. So at the copper anode, we're making electrons. You have the solid copper going to copper 2+ and 2 electrons being made. And so these electrons then are flowing from the anode, going through the voltmeter, and then to the silver cathode. The voltmeter tells us the potential of the cell, which is a measure of energy. At the silver side, those electrons enter and react with the aqueous silver to form solid silver metal. So now as this reaction is happening, as the oxidation keeps occurring, we end up with this buildup of positive ions on the anode. We get all these copper 2+ ions building up. And then on the cathode side, the area around the cathode is becoming deficient in positive ions because those positive ions are grabbing the electrons and then condensing onto the already solid silver cathode. So this is where that, in this case, sodium nitrate part came in. This is called a salt bridge. And so this gives additional cations and anions needed to keep balancing out the charge differences and complete the circuit. So it's just keeping those charges equal and keeping it going so you don't get a deficit where the reaction will stop. So the salt bridge itself is porous and it has a concentrated salt solution, usually sodium nitrate or potassium nitrate. The anions from it go to the anode to neutralize that positive charge buildup, and the cations are going to go to the cathode to replace the cations that are being consumed. So this keeps electrical neutrality and keeps the circuit complete to allow current to flow. So we use cell notation now to describe what is happening in a galvanic cell. What is oxidized starts on the left and what is reduced goes on the right. We use single vertical lines to represent a phase boundary, for instance, maybe liquid to metal or liquid to gas. We use a double vertical line to represent the salt bridge. We do not include spectator ions. We are only looking at what is actually reacting. Sometimes the concentrations of the ions are included. So looking at the copper-silver reaction, the net ionic equation is there. And so what we do is we start with the oxidation half reaction. So in this case, it's copper being oxidized. So we could say copper, solid, and that's one phase. So then it's separated from the other half reaction for the copper. So we would have copper 2+. Well, that's a terrible looking U. That is not Ca. We did not make a new element, sorry. Okay, so there is our oxidation. And then we draw 2 vertical lines to represent the salt bridge. And then we're going to go ahead and do the reduction. So this is going to be Ag plus, and then separated with Ag solid. If you wanted to write this using the concentrations, and you can do it with just the whole aqueous solution, you wouldn't put like Cu2+ and then NO3-, but you could also write it like this. Copper solid, and then we would say Cu 1 molar CuNO3. Oh, let me redo this where I have room again. Okay. Copper solid 1 molar CuNO3 2 aqueous. Salt bridge, 1 molar AgNO3 aqueous. Separation Ag solid. So that works too. Either of these types of notation are completely fine. The one where you put the concentration and having it as the whole solution aqueous is kind of nice because it gives you a lot more information. So that's probably better and a little easier for going back and referencing data, for instance. Okay, so in the next picture, we're going to see another type of galvanic cell where you have a solid magnesium ion and aqueous magnesium chloride. And then the other side, the cathode side, has iron 3 chloride and iron 2 chloride. Both are aqueous. And then they have a platinum cathode in them. And notice platinum isn't doing anything in this reaction. It's all between the iron and magnesium. So the platinum is an inert electrode. So it's going to provide or accept electrons to the redox species in solution. Okay, if you were to have an electrode that is part of the redox reaction, that is an active electrode. So here's that setup. The platinum cathode, again, is not really taking place in the reaction, but it's accepting the electrons for the solution. So it's inert in that it's not actually part of the reaction. If we wanted to write the cell notation for this, have Mg solid, okay, and it goes 0.1 molar MgCl2. So there's our first side. And then the right side, we have 0.2 molar iron 3 chloride. That's being reduced. Sorry, there's no boundary here. We put a comma because these are in the same phase. So it's not a boundary because they're both aqueous. 0.3 molar iron 2 chloride. And then we have a boundary for the platinum electrode or cathode. So there's the cell notation for this circuit. So just to kind of summarize with the galvanic cell, we use compartmentalizing. So the oxidation and reduction half reactions are compartmentalized into half cells. So we have a spontaneous redox reaction to be a source of electrical energy by generating electrons. You have on the left side your anode, where oxidation is occurring, and then the cathode on the right side where reduction occurs. Each half cell has an electrode that is dipped into an aqueous solution, and those half cells are joined by an external wire for the electron movement and a salt bridge to facilitate ion movement. So let's go ahead and look at an example for writing a galvanic cell schematic. We're told a galvanic cell is fabricated by connecting two half cells with a salt bridge, one in which a chromium wire is immersed in a 1 molar chromium 3 chloride solution, and another in which a copper wire is immersed in a 1 molar copper 2 chloride solution. Assuming the chromium wire functions as an anode, write the schematic for this cell along with the equations for the anode half reaction, the cathode half reaction, and the overall cell reaction. So I think it's a good place to start by doing our cell notation. So the nice thing is they're also telling us that the chromium is the anode. And remember, electrons flow from anode to cathode, and we put the anode on the left in our cell notation. So we have chromium solid, and it is in a solution that is 1 molar chromium 3 chloride. And we have our salt bridge to connect it with the other side, which has 1 molar copper 2 chloride, separated because we have a solid copper cathode. Now, when you're writing these cell schematics, one thing that always helped me when I was learning these, because I always wanted to write the metal first on both parts of it, And then I went, oh, you know what? I think of it as kind of a sandwich. I have the metal. It's like the hard part, the bread of your sandwich is on the outside. And then your like mustard and mayo for a sandwich, your aqueous part is on the inside. I don't know if that helps or not. And then your bologna or cheese or whatever's in your sandwich is your salt bridge. So here's your bread, your sauces. Or think of it as like a hamburger, I guess. 1 sauce, 2 sauce, and then there's your patty. I don't know. I don't know if that helps at all, but there you go. There's my weird way of thinking. So by writing this cell notation, though, we can go ahead and write our half reactions because now we have it compartmentalized already. So we know at the anode we have solid chromium that is oxidizing to chromium 3+, and then 3 electrons, right? Because that chromium chloride is broken up, and that chromium has to have a 3+ charge to balance the 3 negative ones from the chlorine. And then at the cathode with the we have copper 2+ being reduced, and it's gaining 2 electrons to form solid copper. Notice we don't have any hydrogen, we don't have any oxygen here. The only thing we really have to balance here are the electrons. So we need to then multiply the 3 by 2 and the 2 by 3. And then we can write, and then we can see that the electrons are going to cancel out. So then we end up getting 2 Cr solid plus 3 Cu2+, going to Cr3+, or 2 Cr3+, plus Cu solid, 3 Cu solid. And there we go. So even easier to balance these redox reactions, assuming you don't have hydrogen or oxygen, which you still might in some reactions, but galvanic cells are, in my opinion, a bit easier and a little more fun to work with.